So welcome to the pre-class video assignment for section 2.2. Here we're going to start looking at solving homogeneous linear equations, second order. This ends up being fairly easy to do. Takes a little explanation, but what we actually have to do is not too difficult. So let's take a look here. Basically, so we are looking at solving homogeneous second order. So this is something like this. In this case, we are looking at constant coefficients only. This makes it a little easier still. This is our most common case here. But we have something like this where A, B, and C are constants. So we could ask ourselves, well, what kind of function Y could this possibly be? The idea would be I have to add together a second derivative, a first derivative, and the function itself, and they have to somehow cancel each other out and give you 0. So for example, this could never be a polynomial. For any polynomial, if you have a polynomial of a certain degree, the first derivative would be one degree lower, the second derivative is 2 degrees lower. There's no way for those lower degree polynomials to add together and cancel out the higher degree polynomial. This just cannot be a polynomial. So there's sort of limited possibilities if you think it through. And the sorts of things that might work here, you might guess, are things that are exponential or possibly trigonometric in nature. So just loosely speaking, if y was sine, or maybe some combination of y and cosine, then the first derivative can be cosine and sine, and the second derivative would be sort of back to where you started with, right? So if you have y is sine, first derivative is cosine, second derivative is back to sine again, these are at least the similar sorts of functions and have a possibility of canceling each other out, or possibly, again, as we will see, our best guess is probably exponential functions. So here's a little insight into how we actually go about solving them. Solving these things involves finding or looking at something called the characteristic, or sometimes called the auxiliary equation for a DE. This is actually fairly easy, but let's just take a look at an example first. So let's suppose we go ahead and assume we have some sort of exponential function as our solution to these things. So let's assume that y equals e to the mx is some sort of function. Let's assume that this is a solution function. Let's see what has to be true about m for this to work. So in order to plug it into our DE, I would need to find the first derivative. So the first derivative of e to the mx would be a little chain rule, m e to the mx. The second derivative is going to be m squared e to the mx. If you plug those into our DE, we would get something like this. Again, if we assume e to the mx is a solution, then this has to be equal to 0. And then notice that you can factor out e to the mx, and we end up with this little equation here, that either e to the mx is 0, which never happens because e to the mx is always positive, or we would need that am squared plus bm plus c be equal to 0. And so this is a quadratic equation that basically tells us what has to be true about m in order for e to the mx to be a solution. So this is called the characteristic equation. I'm here using the letter M. The website sometimes uses the letter R instead of M. But again, the choice of letter here is not super important. So it turns out that if we can solve this second order quadratic equation, if I find the roots to this equation, then we take those roots, plug them into y equals e to the mx, we plug them in for m, and we have identified some solution functions. So roots to this equation, so if we solve this and get roots r1 and r2, then if that were the case, then the function y1 equals e to the r1t, and the function y2 equals e to the r2t, these would be two particular solutions to our differential equation. So that is a little idea of one way we can find some of these solutions. Then the main idea is that this characteristic equation and the solutions to it, or the roots to this characteristic equation, basically determine the solution functions to a differential equation of this sort, which is the second order with constant coefficients, homogeneous. All right, so some questions to give this a go, try this out. So the first one is to find characteristic equations and find the roots of it. The second one is really just going to directly ask you for the roots. So give those a go. All right, then. So this is sort of the big picture so far. The nature of the roots to the characteristic equation is actually what tells us the nature of the solutions to the DEs of this sort. So that is the big picture here. So let's take a look at this a little bit here. We're going to take a look together here now at the easiest case. Case one, we'll call this the easiest case that we'd run into in terms of the nature of the roots to the characteristic equation. So the easiest case is where you solve this characteristic equation, which is a second order polynomial equation or a quadratic equation, and you get two different real valued roots. Call them M1 and M2. So when we get M1 and M2, as mentioned earlier, we can set up two particular solutions like this. And then what we notice is that if M1 and M2 are different numbers, which we claim they are here in this particular case, then y1 here and y2 here, these will be linearly independent solutions, which is a nice situation, as we learned in the last section. That means we can form a general solution by making a linear combination of y1 and y2. So the general solution here would be C1 e m1t plus C2 e to the m2t. And that's all there is to it. If we can solve that characteristic equation, and that the roots to the characteristic equation give us two distinct real roots, then we can fairly easily come up with the solution. There are two other cases for the nature of the roots. We will discuss that in a little bit in the prerequisite material, but as far as the notes go, let's do some examples of case one. And again, it's fairly easy to do if you know your algebra. So find the general solution of this DE, 2y double prime minus 7y prime minus 15y equals 0. So this is homogeneous, it is second order, and it is constant coefficients only. So all we need to do is come up with the characteristic equation. So notice the characteristic equation, I don't really need to go through this rigmarole of pretending to have a function to substitute in. I can just see it here. The characteristic equation will end up being the 2m minus 7m minus 15. So the degree in the characteristic equation correlates to the order of the derivative in the differential equation. So be careful, 15y would just be a constant 15. So all we really need here then is to ask ourselves, can we solve this quadratic equation? So my usual approach is I usually at least think about trying to solve by factoring first. So take a quick look at this one. This, if it factors, this would have to be 2m and m. And in fact, this one does factor into 2m plus 3 times m minus 5. Again, you can FOIL it back out to double check, but that is our solution. And then I get the two roots. M is minus 3 over 2 and m equals 5. Again, I called them both m. You can think of them as being m1 and m2 if you prefer. Therefore, we know that This is a particular solution. This is another particular solution. And if we form a linear combination of them, we get the general solution. And again, remember from last week that for the last section that, again, second order differential equation, I'm expecting a general solution with two constants in it. And that is what we get here. So we are pretty happy about that. So this was one. Let's try another one. And again, it's much the same, but here's one. If I look at this differential equation, I can fairly easily come up with its characteristic equation. Again, I think about trying to factor first. This one does not factor. So if it doesn't factor, I go straight to the quadratic formula. So apply the quadratic formula here. You should have that memorized. So this is what I get applying the quadratic formula. And I get these rather awkward looking roots. One of them is -5 plus root 13 all over 2. The other one is -5 minus root 13 all over 2. Those are the two real roots here, but they are two distinct roots. They are not the same root. They are two different roots, and hence those give us two particular solutions. Again, one of them is y1 with the plus in it. The other one, y2, has got the minus in it. So these are two linearly independent solutions, and hence we can form a general solution by making a linear combination of those two. And that's really all there is to it. So here's an example on my Open Math to give that a go. Couple of examples there. All right, so that's it for the notes. We will finish this note packet together in class. A couple of prerequisites we need to look at. So again, as we were talking about, it turns out that in this particular equation, in this particular situation where we have let me describe again a second order ay double prime plus by prime plus cy equals 0. When we have a DE of this form, second order homogeneous constant coefficients, it turns out that the roots of the characteristic equation ultimately will tell us everything we need to know in order to solve these DEs, find a general solution for these DEs. We have talked about case number one. In case number one, we ended up with two distinct real roots. So this happens when and you're solving a characteristic equation. So well, this is really just an algebra fact. If we're solving a quadratic equation like this, we know the quadratic formula gives the solution like this. So this quantity underneath the square root sign is something called the discriminant. And the nature of the discriminant basically tells you what the situation is in terms of the roots of the characteristic equation. And that is also then subsequently going to tell us the nature of the solutions to the DE. So in our first case one that we were just looking at in the notes, we had two distinct solutions. Why two distinct real solutions? Why did we have two distinct real solutions? That is because b squared minus 4ac was a positive number. If this is a positive number, taking the square root is still real, and then we get two solutions because we added plus, we've got plus once and minus once. This is why we have two different solutions. So when b squared minus 4ac is positive, we get two real distinct roots. They might be integers, they can be rational numbers, they can be irrational numbers, but you get two distinct real roots. In that case, that was what we just saw, we were able to form solutions. So what we really want to talk about here, or look ahead towards here, is what happens. So the nature of the roots, the nature of the solutions will be determined by the discriminant here. But let's just talk about the algebra of it. If b squared minus 4ac ends up being 0, then this guy here is 0. And then you just end up with a minus b over 2a. So you only end up with one real root. So that is a different situation. And this is what we will look at in our notes as case 2. And then a third thing that happens is if you have b squared minus 4ac is negative, then you have the square root of something negative. That is a complex number. So you end up with complex roots. And that is another case. That is our case 3 that we will talk about in the notes. But we want to be able to recognize these cases. So a couple of examples on my open math to try about that. And there's a second one to try. And then just let's talk a little bit about the complex case. If b squared minus 4ac is less than 0, we end up with 2 complex solutions. So a couple of useful notes about complex roots to a quadratic, or in fact a polynomial equation. Number 1 is that complex roots can only occur in conjugate pairs. And so that tells us that if a plus bi is a complex root, then its conjugate, a minus bi, must also be a root. So you can play around with these and kind of see that this must be true. You can kind of see it in the quadratic equation. But here's a couple of little questions about that. The first one, and then there's a second equation, again, fairly simple, just about complex roots. And then lastly, again, when you solve a quadratic equation with a negative discriminant, you have to end up roots of the form a plus bi. So that is what we're looking for in that third case. So here is another little example. And then last but not least, well, as part of the explanation in this next section and part of the explanation that we have to wade through in order to look at the third case where we have complex roots, we will need something called Euler's formula to figure it out. Again, the bad news is it's the explanation is kind of complicated. The good news is what you actually have to do is fairly easy in order to solve these differential equations, but the explanation is a little tricky. So as part of the explanation, we will need Euler's formula, which says this. That is e to the power of ix is cosine x plus I sine x. What this is very useful for is this is a pretty awkward situation, having a complex exponent, not fun, not nice mathematically. So what Euler's formula does for us is turn a awkward expression with a complex exponent into an expression with a real part plus I times the imaginary part. This is your classic form of a plus bi complex number. So that is what we want here. We will need to do this as part of our explanation. So you're going to have a couple of my open math examples to try here. And really, I just want you to use this formula to simplify some awkward expressions that might look like things like this: e to the 2 plus 4i, or possibly a function e to the 2 plus 4i times t. So you might have to do some preliminary simplification. So notice that e to the 2 plus 4i can be written like this by just exponent notation. Yes, this is e to the 2 times e to the 4i. So e to the 2 is a perfectly good real number. E to the 4i is the awkward complex exponent, and the e to the 4i can be simplified using Euler's formula. So there is an example for doing this with a numerical example. So give that a go. And then the last example we'll look at will be one where we have a function example, that is, we will have a variable up here as well. The process is much the same. I would start by distributing the t, so there's an e to the 2t and an e to the 2t and plus 4it, and then that can be broken apart as e to the 2t and e to the 4it. And then the second part, again, you can work on using Euler's formula. So give that a go as well. All right, so that is it for that video. Thank you guys. We'll see you and finish it up in class.